All right, we're going to continue. Sorry about the short break. We might have another talk being swapped out this afternoon, so everybody knows at 4:30. The speaker got in a bit of an accident, but if we're lucky, he'll come here today. If not, we'll try to fit it in tomorrow. Our next speaker is Colin O'Flynn, who's been with us quite a few times over the last few years. He's the creator of the open source PhyWhisperer project. And last year, if you were here, you'll remember that he was giving a workshop during which he actually gave me this really cool blockchain, which was a chain with a block attached to it. It sounds like he's really advanced his research, though, over the last year, so I'll let him talk about
Thanks
that.
All right, yeah, so thanks everyone for being here. So I'm going to talk to you about breaking a Bitcoin wallet with electromagnetic fault injection. So I have like two kind of official things that I'm associated with. One is PhyWhisperer, the open source project. I had a startup, New AE Technology Inc. At the same point, I'm also an assistant professor at a university on the East Coast in Canada, Halifax, where I live, Dalhousie University. So there I'm working on sort of cybersecurity research, which gives me some more flexibility for doing interesting things. Really briefly, I'm going to go over sort of blockchain and Bitcoin as it's relevant to this attack. This talk is more about embedded security than specific on blockchain and Bitcoin. But basically, for blockchain, you have to remember there's two aspects to it. So the first aspect is the block. So this is like your standard concrete masonry unit CMU block. And then you also, of course, have the chain. So this would be a number 4 chain. You can vary the chain thickness depending on the security you need to achieve. But if you want an example of a real-life use of blockchain, voting security, extremely important nowadays. So if you had a electronic voting machine like this, what you would do is you would take your CMU here, you would then chain it to the voting machine. Now this is pretty good. That would stop one from being removed. But the real strength of it comes when you then chain these together. And you then have a very secure voting system. So don't let people tell you blockchain is just BS for voting security and stuff. It's very useful. It's extremely powerful. And in fact, the first use of blockchain was defensive. So H. Simpson in May 2008 had this implementation here. This was sort of appropriated later to the more popular version that became the computer model. So these dates are accurate. You can check this. This is real history. And it's this implementation that we talk about. This gave us Bitcoin that everyone really knows blockchain for. But it was initially much more a defensive use case. Because we have Bitcoin, we now need to secure them and store them somewhere. This has given rise to a lot of pretty interesting devices, Bitcoin wallets. And there's a lot of really interesting ones out here. So ASIC Vault is one of my favorites, I think, because you'll notice it has 1,000 times stronger security. Very good. And what they've done is they've made an ASIC that hardware accelerates the key derivation function. So if you're a sucker and you're only doing 2,000 rounds of your key derivation, like, come on, when you could be doing 2 million. If someone were to break this wallet, they would need something like an ASIC that hardware accelerated the key derivation round. And where would they find an ASIC that hardware accelerates the key derivation round? Like, you can't get that. They also have some really innovative pricing models. So if you only pay this €10 a month and you're doing 1,000 rounds, why would you do that? When you could pay them €15 a month, or a million, sorry, and do 3 million key derivation rounds. So we have all of these sort of like really investor-friendly things going on nowadays. All right, so why can such crazy wallets exist like this? The real answer is that if you look at stuff like the market out there, one of the larger wallets, Ledger, claimed to have sold like 1 million wallets, and each of those wallets is over $100. And this was last year. So this is like, actually, there's a big market here. This was surprising to me when you look at this. So the one I'm in particular going to be looking at is just one wallet. It's a Trezor. So this is an open source wallet, or open source firmware is available for this wallet. There's several versions of it. And it's a really interesting target. One of the things with all of these wallets is the sort of how you buy it is interesting. Because potentially you're storing millions of dollars of blockchain, but where do you get this wallet? You go on Amazon, you buy a lobster dog toy, you buy a crypto wallet, you buy some toilet paper and shove it in a box and Amazon ships it to you. So you could be buying this from anyone, right? You could also be getting this from a different distributor. The way Amazon does their inventory in the stores, they'll substitute products that have the same SKU from different vendors. There's no, real known method of getting these securely, at least if you just buy it from, Amazon or something. So having different security that actually validates no one's done some sort of malicious attack is important. Because these wallets basically generate a private key. That private key is now the key to all of your Bitcoin money not being stolen. If someone were to load malicious firmware, they could generate known private keys basically and ship them to hundreds or millions of people, and they now know everyone's private keys. So one of the features they list, for example, is like an ultrasound hardware seal, making it difficult to be restored after breakage. So what this looks like, let's see if this works. Okay, so here's one of these wallets, and you notice some tooling marks on it because this is the first one I got, and I said, well, how difficult is that to break this ultrasonic seal? And you can see it's very not difficult. This one's been broken, obviously, but you could reasonably, I think, open these up and seal it back if you were more careful than me with it. So that's sort of where the state of a lot of these tends to be. All right. So why pick on Trezor for this talk? There is other ones, as I mentioned. The ability to use the open source code is really important because I'm going to be showing you how some of these attacks can apply to general embedded systems. Because we have the source code, we can look at it, we can modify it. It makes it a much more interesting target. I also will note that this particular problem was in a firmware patch that they've already deployed, so if you had a wallet and you've done the firmware update for it, this exact attack wouldn't work for those. All right, so to understand the attack, we first have to talk about the recovery seeds. I mentioned that there is a private key generated by the device. They tell the user what that private key is, so the user can write it down in case they lose the wallet. This is called the recovery seed, so this is from their documentation. That recovery seed is basically very critical, and it displays it as a series of English words. So rather than writing down some big hex numbers, you write down a series of English words. There's an additional option they call it a password, but basically what this password is doing is it actually uses some other data you input to generate the actual private key used for the wallet. What this password protect mode means is that all the secrets are no longer stored on the device, which is very good. Because what I'm going to be attacking is the fact that the secrets are stored on the device, and we can extract those secrets and then get all the Bitcoin. So this is what the inside of the Trezor looks like. You have a microcontroller right here, and this microcontroller is basically everything about the security of this device. That microcontroller is not a secure element, secure device. It's sort of a standard microcontroller that you could buy is well known in embedded development and stuff like that. The important part, right, is that if you knew this one microcontroller had $10 million of Bitcoin on it, it's sort of a non-issue to say, okay, great, I'll get that money out, therefore I should spend $10,000 or whatever it is to do any sort of advanced attack. So even if the stuff I'm talking about didn't work, it's important to realize that fundamentally there's kind of some questions about if you're going to be storing a ton of money on a device, should it be a $9 microcontroller that everyone can buy and attack easily? This talk itself is basically an extended / ripped off version of another talk that Dimitri and Thomas gave at CCC, as well as another guy, Josh Dacko, who's not here, so we don't mention him. And you're going to have the chance to vote later because they're going to be giving their presentation, I believe. Yes? 4:30. And then we'll have an audience applause for which Bitcoin presentation is better. And so their talk, I'm going to summarize now to set the mood. It had vulnerabilities on several Bitcoin wallets, so not just one wallet like I'm doing. For the Trezor specifically, as you'll find out, you needed physical access to the PCB. I showed you there, you could open it pretty easily. And once you had that physical access, it was performed with pretty high reliability. The real fundamental difference is that their attack is looking at getting the key out of SRAM. Because during the update process, the important data is copied from flash memory to SRAM, you dump the SRAM, you get all the important data out. And so this was Dimitri telling me on like December 17th about how all the data is just stored as ASCII strings in the SRAM and you can just easily dump it. So this was also not ideal being told on December 17th for like a relaxing Christmas with my family, because then they were less impressed when I'm wanting to do all this sort of work instead of Christmas things. All right, so now we want to get the recovery seed out. So we know one way to do it is with dumping the SRAM. What else could we do? And what I was particularly interested in was reading it directly out of flash memory, because one countermeasure that could be rapidly deployed was to say, okay, we're not going to copy it to SRAM during the update, we're going to leave it in flash memory and just not erase that section. So I kind of wanted to also demonstrate that just patching one little area isn't a good idea. And what I looked at in particular was this. So this is the secret data. This is a memory map of the device, by the way. So one of the nice things, because the software is open source, this table here was copied from their source code and put in my slides. I didn't do any fancy reverse engineering or anything like that. So we have this secret data stored in the device flash memory. Before that data, we have this bootloader code section here. So this code section is where the bootloader is running. And that's what I wanted to look at, because with fault injection, often one common attack is to do something like start reading from memory and just continue to read well beyond the end of the buffer. So if there's something in the bootloader section I can perform that trick on, it would mean I would get access to this secret data that I really want. So part of USB, really briefly, they have this idea of USB descriptors. USB descriptors, when you plug your thing into your computer, it tells the computer what it is. These descriptors are just like big chunks of data that are stored in various structures, and they identify different things about the device. When the computer asks the device, what are you, what interface do you talk on, it sends this get descriptor request, so this is just a standard request. The only important part to know about this descriptor request is that there is a field called W-length. This is 2 bytes, so 2 to the 16, and the computer requests as much data as it wants about the descriptor. The device will only send back as big as that structure is, but the reason we have this is frequently what happens, the computer first requests, I would like 8 bytes of the descriptor. Okay, now I know what the descriptor is, I'll request the rest, or I won't because I don't need this descriptor. So everybody has to process this value in the USB stack. This is in every USB stack, including this little Bitcoin wallet that has a firmware update in the bootloader. And here is where this processing happens. So what we basically have is, this is the data being sent back to the computer from the Trezor wallet. There's basically a pointer to the data structure, and there's this little comparison here that says, well, I either have to send back the minimum of the size requested, which could be like 8 bytes or something, or the total size of this structure, which is 100 and some bytes long. So if the computer requests FFFF as the length, then I'm only going to send back 197 bytes, or whatever the size of this structure is. If the computer requests 8 bytes, I send back 8 bytes. Where the fundamental attack comes in is that this is implemented or compiled roughly as you expect. So it preloads the value from the host computer into a register. It's then saying, hey, is that register too big? Is it larger than this hex 92 size of the struct? If it is, well, we're going to just copy the maximum size back into our register. So what's going to happen here is that if we could skip this, all of a sudden, it's going to just take whatever amount of data I request. I request 65K of data. It's going to send back 65K of data. And this is where we want to do the attack, because if I request the descriptor and the remaining data after it, that includes this sensitive metadata. This is really powerful for embedded systems because there's a lot of interesting stuff in embedded systems within 65K. Some embedded systems, that's basically their entire memory space. In this case, the sensitive data happened to be around one of the descriptors, so it worked really well. But as step 0, being really lazy, we can get the open source code, we can compile it onto a version of the wallet. So this is, I've just taken a wallet and soldered a new chip on, so I have full JTAG access. And we can simulate this glitch. And by simulate, I literally mean like single step through, you hit that comparison, and I use a debugger to skip that check. When you see that, you say, okay, yes, I'm going to get back 65K of data. It's good. And I also confirmed that in that data there is this recovery seed that's all in strings. So if I look at the strings, I know I'm going to get this to work. So this isn't the real attack yet because it's just me simulating it. So how we're going to do the real attack is electromagnetic fault injection. Very briefly, what we do is you have a loop of wire. You pass a really high current through this wire, or a fast-changing current, to generate a fast-changing magnetic field. If you have another wire nearby, so we get a good strong field here, another wire nearby, such as you might find inside the chip itself, this will generate a small voltage on that wire. That voltage change is enough to flip the state of bits within the target device. So this means we could do stuff like change instructions, mutate them from like the load to a no-op. We could do stuff like cause data not to be loaded in time so the results of the comparison are incorrect, or anything like that. In our case, we just want it to end up giving us this, this result that skips the check. As a side note, when you describe EMFI, what you'll notice is most of these tools put like a high voltage. So how they work is they have a big capacitor bank. And there was a talk, if you remember, 1 or 2 years ago, BadFet, that was basically an open source EMFI type tool and using really high voltages. Why do you need a high voltage? Because all we need is strong current. Basically, the magnetic field is related to how quickly we can change the current through the coil. However, it's also proportional to how many turns of coil we have. The inductance of that coil increases with the number of turns. A higher inductance basically makes it much harder to change the current quickly on a physical level. So you have this annoying balancing act between wanting a super high number of turns to get a really strong field and wanting only one turn to be able to change the current very quickly. What you sort of find out as you experiment with this is there's a sweet spot kind of between 60 to 500 volts. So you'll see most EMFI generators using this higher voltage. So what I have to perform this is basically there's a wallet here. I force bootloader mode with my very high-tech screws pushing the buttons down. And I then have a coil tip that's positioned over the case. So this is over, nothing's broken the enclosure at this point. So you know, if you really carefully inspected this, besides maybe some marks from the clamp, you would never be able to notice. So if you put some tape on that, you could avoid that. And what I'm using to trigger it is I use USB data. So I have a total phase Beagle 480. This is a USB hardware sniffer. It has this feature that we can say, hey, trigger on some data. In this case, the data is, you know, when I was showing you that get request USB standard spec thing, basically I'm just triggering on that message going across the wire. It goes across the wire, the device is going to process that at some point later in time, so I know if I insert a glitch, if I get lucky, I'm going to hit that that exact moment. It's not super reliable for timing. There's some jitter due to a queue that processes the message on the Trezor side of it, so it's not like I can get 100% success rate. But you know, if it works once over an hour, then you can just dump everything, or you do get a dump of everything. So you only really need it to work once. To simplify this further, I have sort of a coming soon, and this repo is active now, so you'll see development of it happening. Something I call PhyWhisperer USB. The idea of this is there's a USB Phi chip that sits in between a USB cable, and the idea is to let you do types of attacks like this without using the total phase. And it's fully open source hardware and software. The main advantage is you actually have a power switch with an ability to discharge the target. When you're doing this fault injection, you need to power cycle the target every time to get it back to a known state. And so this tool is something that basically I ended up needing as part of this work. You could potentially use it as something like a sniffer for USB. Because it's physical layer, you do see error packets. Error packets are super handy for this work as well, because when you reset the target, you can figure out where in the USB stack it is, because if you see it reset, you know it processed so far and then bailed. So it's like, okay, it processed the setup phase and the data zero phase, but then there's no transactions afterwards. Like right here, there's an input transaction after the setup phase that's missing on the red one, basically because the device reset. So I know it at least got that far in the processing. So there's actually a lot of use that having the error stuff is valuable for. The idea of this is not to inject packets. Theoretically, it can do some of this, but there's better tools for this. So if you're using something like FaceDancer or now GreatFET, that's really designed to do the type of USB fuzzing. This is really looking at physical layer effects and physical layer triggering that we can get out of having a USB PHY and an FPGA together. So this is what the current setup looked like without the PhyWhisperer in there, where I did have the Beagle generating a trigger. This trigger is routed through a chip whisperer. I just use the chip whisperer as like a FPGA board that can generate a narrow pulse at a fixed offset, and then sweep that offset through various times. So that's then routed to this device here, this EMFI generator, the chip shouter, which then inserts EMFI into the device. As I mentioned, we need USB power switch to turn the device on and off, because I'll show you in a second here, it crashes very frequently with this type of attack. All right, let's see this. So here's a unbroken Trezor, which if we plug in normally, so there's an unbroken Trezor, and if we hold these two buttons down, it enters basically the bootloader mode. So you can see it's in the bootloader mode. This device then, let me just move this back up. This device now, I can sort of insert fault injection by just sort of holding down this button and moving this around. So what you'll see is you see some like various error messages coming up. So they do have some countermeasures against, invalid errors. So there you see it says like stack smashing detected. And so this is because it's actually, I happened to hit a point in time where it was able to get like trigger the stack smashing detection. And so you'll see other errors come up. So it says, please unplug the device, but we can just reboot it with the EMFI. There you go, hard fault detected. And occasionally what you see, actually an interesting one, is you'll see like that's a different error. And because you saw for a second it was giving an error that the, unofficial firmware detected. And so it's somehow corrupted. In fact, it seems to be missing some characters. It's somehow corrupted that value. So if you do this enough, it sometimes can permanently brick it. Oh, there you go, memory fault. Which I don't want to do, because so Trezor gave me a 1 Bitcoin for disclosing it to them, and it's stored on that wallet. So I didn't buy another one. Okay, let's move this. Also, don't let Dimitri have that wallet. Okay, how to fix it. So basically, why can you send back 64K of memory? Number one, that was the thing. No descriptors are that big. So I mentioned that I wanted to check that worked with my simulated effect, specifically because I thought, hey, maybe they limit it to only sending back 256 bytes. So you can just mask off the return W value to ensure nobody can get a full 64K of memory, because that's not needed for these stacks. We can armor the sensitive data, right? So we know where the sensitive data is in memory. We can either use the memory protection unit that's in this device. Like there's no OS or threads or anything doing this automatically. But we can do stuff like set that whole section as invalid when nobody should be reading from it, and then set it as valid again, as well as keeping like invalid sections around that buffer. So there's a lot of stuff like that we can do. That's actually basically free. The chip already can do that, so if we just turn on those features, it can be really useful. You can try moving the memory layered around. In this case, I attack the bootloader, because that could then read into the sensitive memory. What you have to remember is we might be able to corrupt a pointer. So you saw it was also loading the location of the pointer in a register 2. If we corrupted that, we'll actually get it to read other memory. So when you're doing this glitch, you do see occasionally other memory coming back that's not that's not starting at the USB descriptor. The final thing is encrypting data, at least at rest and possibly in place on the flash. So one of the things is, right, and I don't know why dumps in quotations there, that's not supposed to be. So don't allow this memory dump that you can just use strings, just like, oh, there's the good data I want. If this was, somehow encrypted, it would be very unclear what was sensitive data and not. So a number of those fixes were pushed into the latest firmware. So what's released now basically has some of this protection built in. So the same sort of attack would not work on a current model that's been updated. The other thing is, again, because if you used a passphrase, not all the secret data was stored on this, so it's not possible to break a device or recover the information from a device that did have that passphrase feature turned on. Yeah, so that's sort of it. That's what I wanted to show you about. If you're interested, so my website, oflynn.com, has sort of a blog post with some more details of the physical setup, and there will be a paper coming out at some point with a few more details on that. If we have like a few minutes for questions, we do? Okay. If there is any questions, and if you have hard questions, you can ask Dimitri and Thomas later. Nope. All right, thank you very much.